Hey, chemistry crew, Mr. Collier here, and today we're going to talk about acids and bases. You can follow along in your notes packet. So the first thing I want to talk about is a quick review of how we name acids and bases. So we did this back in our naming chapter, but the first thing is my acid or base binary, or does it contain a polyatomic ion? If it's binary, what we're going to do is we're going to take the prefix hydro and tack it on to whatever the anion is. In this example over here, it's chlorine, right? So H hydro, chlorine gets the anion name with the ic ending instead. So this is hydrochloric acid, right? Hydro for the H because it's binary, and then chlorine becomes chloric. Here, this one, it's called hydrophosphoric acid, so that's going to be hydrogen and phosphorus, and then we just need to figure out how they combine. Phosphorus has those 3 electrons that it wants to give, or spaces that it wants to fill, and hydrogen has that 1 electron it gives, so you need 3 hydrogens for 1 phosphorus. Now, if it is polyatomic, meaning it's hydrogen with some polyatomic ion, we're not going to use the prefix hydro. We're going to look at the ending of the polyatomic ion. So if the polyatomic ion's name ends in ate, we're going to turn that to ic, and if it ends in ite, we're going to turn that to us. So here we have SO4, right? And since that is sulfate, we're going to just change this to ic. So instead of sulfate, it becomes sulfuric acid. Here we have sulfurous acid, which means that must have an ite ion, which means this is hydrogen and sulfite. So hydrogen and sulfite. We're still crisscrossing oxidation numbers to determine the formula. So that's the quick review. So I'm going to use acid names. Now you can recall how they're named and how their formulas come from those names and vice versa, how they're related. So the first thing to talk about with acids and bases is that they are solutions that have some pretty common properties. So acids tend to taste sour. Now, in a lab, you shouldn't go tasting things to determine whether it's an acid or a base, but like when you're eating food, you might notice that we actually eat some common things that are acids, like lemon juice or whatever. Bases are going to be bitter, which is a subtle distinction, so it's not always helpful to some people. But when it comes to what they do, they're a lot more distinct. Acids tend to look like water, but they will burn or sting if you touch them. Bases can also look like water. Again, these things are solutions, so the most common types of acids and bases are just chemicals that are dissolved in water. But bases tend to feel slippery, okay? And so that's something that with household chemicals, you might know you have a base if you can feel it and it's got that slick feel. Another key thing, and this is a test we do in a lab in class, is acids will react with metals while bases will not. And when they do react, it's a replacement reaction where you get hydrogen gas coming off. And acids will act as an electrolyte in solution, but so will bases. So that right there is not necessarily an indicator. Both acids and bases are things that tend to dissolve and become electrolytes. So the next thing I want to talk about is how do we know whether we have an acid or a base? And this is something called an indicator. An indicator is some chemical that will change color in acids or bases. So the first is litmus paper, and there are 2 types of litmus paper. These are little strips of paper that have been treated with a chemical, and if you have blue litmus paper, it will turn red in an acid, and if you have red litmus paper, it will turn blue in a base. So red acid, right? Red ends with a D, acid ends with a D. That's the color you get when you have an acid. This is just a pretty handy, quick test to see if you have an acid or a base. It's so handy that it's actually become part of our everyday language. Someone will say, oh, it's a litmus test for this, just meaning like, if this is a true, then you know you've got this thing. That's what litmus tests do. They test to determine whether you have an acid or a base. The next up is phenolphthalein. This is a super common, although hard to spell and say, indicator that is colorless in an acid but turns pink in a base. It's an amazing color change when you see it in class. It's pretty cool. pH paper has a little bit more versatility because it can change a range of different colors based on whether you have an acid or a base to tell you whether you have an acid or a base and how strong that acid or base is. We can also use pH meters similarly, where we can actually get like a digital readout to tell us a little bit more specifically. So there's different things varying from just a general test to pretty specific tests to tell us about acids and bases. Now, we also mentioned acids and bases earlier in the year when we talked about types of reaction. We can have a neutralization reaction, which is a reaction between an acid and a base where they will neutralize each other. And this is going to be basically a double replacement reaction where you end up neutralizing the acid and base because those two ions are not doing their own thing quite the same way with the same properties, and so you just get water and a salt. So here we have hydrochloric acid, sodium hydroxide. The ions are going to switch place, and when you get hydrogen bonding with hydroxide, oh, that's HOH, that's just water. So that's where you get the water. And then here we would have sodium and chlorine giving us sodium chloride. So that would be a neutralization reaction where you start with an acid and a base, you end up with a salt, and you end up with water. Next up, I want to get into a little bit of the definitions of what these acids and bases are. So there's a couple different ways to look at this. The first is the Arrhenius definition, which is kind of a nice starting place to understanding acids and bases. Acids, when they dissociate in water, that means they split apart into their ion, they produce hydrogen ions, H+. So that's sort of one of the simpler ways to think about this, is just an acid is something that has some hydrogens that when you put it in water, those hydrogens are available for bonding. Whereas a base, when it dissolves in water, dissociates, it's going to have hydroxide ions, OH-. And you can tell, just like chemically, that these are going to be able to do different things, kind of the opposite things, right? Hydrogen's got this positive ions floating around, and hydroxide's got these negative ions floating around. Now, the problem with this particular definition is it restricts the acids and bases to just things dissolved in water. And while that's the common starting point to studying acids and bases, it's not the only types of acids and bases. And so it kind of also oversimplifies it, just saying that when these things dissolve in water, there's just hydrogen floating around and hydroxide floating around, which we'll talk about is not quite exactly the case. And so there are certain things that don't quite fit, like ammonia. And so we have to come up with maybe another working definition. And so our next working definition is going to be the Bronsted-Lowry definition, which is that an acid is a substance that can donate hydrogen ions. So example, hydrochloric acid has these extra hydrogen ions that it can donate, and a base can accept those. And that gets away from the behavior in water, because now we can include something like ammonia, which can accept a hydrogen, doesn't necessarily have to have hydroxide, and still act as a base. It focuses exclusively on what those hydrogen ions are doing. Okay, and something to consider here, right? I'm using the term hydrogen ion, but really that's just the equivalent of a proton, right? So acids are often referred to as proton donors and bases as proton acceptors. So really what we're looking at is substances that can move around just a single proton, right? That positive charge. Now, what actually happens in the water is that a hydronium ion is going to form. And what a hydronium ion is, right? It's an ion, so it's something that's charged. And hydronium is H3O. So this can be used to more accurately portray the Bronsted-Lowry definition. We can talk about, instead of simply the hydrogen ion, we talk about the actual hydronium ion, because that tends to be the thing that's forming in water. You've got, if something is donating an extra hydrogen, you're getting these hydronium ions forming. Now, here's just a vocab term that'll come up as we get deeper into acids and bases. Amphoteric is something that can act as either an acid or a base, and we're going to see that water actually does this, because water can gain a hydrogen ion, and that's like what a base would do, and become hydronium. Or water can lose a hydrogen ion, become just the hydroxide, OH, and act as a base, or acid, sorry. So when something is an acid or a base, it can be stronger or weaker, right? So something can behave more like an acid or less like an acid. And the same thing with bases. And that has to do with how it dissociates in water. We represent this by the arrows in the chemical reaction, even though technically we're just drawing kind of how something dissociates in water, how it dissolves. So something with a single arrow is dissolving pretty much all the way, right? So HNO3, you pretty much exclusively get this NO3 ion, and you get those hydrogens floating around forming hydronium. Whereas if we have this double arrow, that just means it doesn't quite dissolve all the way. So you're still going to have some of the original. It's not so dissociated. The ions are happy to kind of go back to their original state if they find their buddy, and it's not quite as strong. So we can have weak acids and weak bases, or strong acids and strong bases. We'll talk later not just about the strength, but also how we measure those things. One thing, I just want to mention this briefly, it's something that really makes more sense in person to talk about, is conjugate acid-base pairs. These are pairs of compounds that differ only by a hydrogen ion. So when an acid loses a hydrogen ion, it becomes a conjugate base, and when a base gains a hydrogen ion, it becomes a conjugate acid. Again, it's something that we will look at in person. So here you have two things. You have an acid, and then, in this case, water is acting as an acid because it's giving a hydrogen to this ammonia. And so when it loses that acid, it becomes OH, which is what we call its conjugate base, because now it's different from this original thing by simply a hydrogen. And it could go back if this dissolving, or this reaction, if you will, reverses. Same thing here. This base, because it gains a hydrogen, could act as an acid if it loses that hydrogen. So it's just things that differ by a hydrogen, usually on the left and right of a dissociation. And we can just refer to that. All right, I believe that is where we're going to stop for here. Let me know if you have any questions, and good luck.